Hello, and welcome to my presentation on hydrogen and carbon monoxide mixture as a replacement fuel for the production of renewable electricity within gas turbines. My name is Caleb Scott, and I am a member of Project Group 3. So to begin with my table of contents, the objectives of this proposal, the research justification, the experimentation, deliverables, future research, and conclusion. The first and main objective is to replace the use of fossil fuels with a hydrogen and carbon monoxide fuel mixture. The second objective is to identify the thermodynamic properties of the proposed mixture by modeled experimentation. And the third objective is to compare data of the proposed fuel with data from modern-day gas turbines. To justify this research, one can look at the power generation statistics within the United States. Figure 1 is showing that the orange line and the green line are coal and natural gas respectively, which are fossil fuels. As you can see, those are much higher up on the y-axis, which is 1,000 megawatt hours. So those are being used for power generation way more than nuclear, hydroelectric, wind, and solar. The byproducts from the combustion of fossil fuels have been proven to be harmful to the environment as they are considered a greenhouse gas. A greenhouse gas is just a gas that traps heat in the atmosphere and can lead to climate change. The benefit of the proposed syngas mixture is that the byproducts are water and nitrogen, which are not harmful for the environment nor human consumption. The campaign Clean Energy for All is backed by hundreds of companies and thousands of citizens who have pledged to get rid of fossil fuels and to take on clean energy as 100% of power production by the year 2050. So for experimentation, the experiment will be carried out using a scaled-down combustor basket. It will be similar proportionally to a full-size gas turbine combustor basket. The reason for the scaled-down combustor basket allows the observation and estimation of how the syngas would react under combustion for a full-size combustor basket. We'll do this by supplying hydrogen and carbon monoxide to the model combustor basket and igniting it using a pilot nozzle. This is the same process as a traditional gas turbine. The temperatures of the pilot nozzle, the outlet of the combustor, as well as multiple points on the combustor shell will be measured using thermocouples. And we will collect this data for the mixture performance while being combusted. As you can see in Figure 2, the pilot nozzle is essentially just a spark plug for the combustor basket. Figure 3 is the combustor basket. This is a full-scale one from a gas turbine. And Figure 4 is a thermocouple, which will be used to detect temperature on various points of the basket as well as the pilot nozzle. The timeline for experimentation, the first 10 days will be used to procure a scaled-down combustor model, followed by 20 days to find a vendor to manufacture the model, which will be a tough task because we only need a quantity of one, and most vendors do not like to only make one quantity. There will be 30 days for setting up the experimentation lab that can safely provide hydrogen as well as carbon monoxide, 60 days for the actual experimentation, trying different mixture variations, 10 days to analyze the data from experimentation, and 5 days to create a relation that illustrates the fuel mixture in its regards to proportions. So to better explain this, the deliverables, when a successful fuel mixture is identified from the experiment data, the mixture proportion will be put into a relation. The relation will be used as a baseline for future design that pertains to combustion from hydrogen and carbon monoxide. And the relation will just show the best portion of each gas for optimal efficiency. That's also the main research question, to find out the best proportion of each gas for the best efficiency. And the combustion properties of the gas mixture illustrated with data from thermocouples, so the data recorded will be taken from the thermocouples and made into the relation. For future research, the transition from fossil fuels to the proposed syngas mixture will have to be researched for every single model of different gas turbines. Every model of a gas turbine is different, so it'll have to be researched in each different aspect. And using the final gas proportion relation to apply to other engines such as cars, industrial machines, construction machines. Continuing the research for the longevity of the equipment used within fuel consumption of the proposed syngas will have to be continued to be researched. And create more efficient means of producing hydrogen. Hydrogen is the main fuel for the proposed syngas mixture, so it is important that hydrogen is readily available and environmentally friendly. In conclusion, a hydrogen and carbon monoxide syngas mixture can be used as a replacement for fossil fuels. It supports the drive towards clean, renewable energy, and it also promotes future education and research into the field of renewable energy sources.